Hello and good afternoon, everyone. Hope you all doing well and safe. Now I request Mr. J. Arunraj Kristudas, Assistant Professor, Department of Civil Engineering, SRM Valliammai College, to welcome the gathering.
Good afternoon to everyone. I welcome you all for this technical talk on challenges in fluid mechanics organized by Faculty of Civil Engineering and Industry Institute Partnership Shell in association with IST and IEI. It is a red letter day in the history of our civil department. I am honored to welcome our chief guest, Dr. Subashisa Dutta, Professor in Civil Engineering Department, IIT Guwahati. Thank you, sir, for accepting our humble requesting. I welcome you, sir. I would like to welcome our extended principal, sir, Honorable Vice Principal, and beloved head of the department, Dr. D. Elango, sir, under whose guidance and support this session has been organized. I would also like to welcome all the faculty members, dear students, and external participants who have joined with us today.
Thank you, sir. Now I welcome Dr. A. Lima Rose, Associate Professor, Department of Civil Engineering, SRM Valliammai College, to introduce our guest speaker.
Good afternoon, children and all. It's my great honor to introduce our guest speaker for today's session, Dr. Subashisa Dutta, Professor, Department of Civil Engineering, IIT Guwahati. Sir has started his service SRF at UST College of Engineering, Sambalpur University. After which Sir has put his enormous effort as scientist towards ISRO Space Application Center. Since 2007, Sir has been serving this academic sector at IIT Guwahati. Sir has an excellent record of project and publication works, which has been major strength and support to the academicians and budding engineers till date. Sir has guided a large number of students to complete the thesis for PhD degree. His intensive contribution towards research under various domains such as hill slope hydrology, distributed hydrologic modeling, climate change, bank erosion, fluvial hydrology, and geoinformatics were successfully achieved and was published in various national and international journals. Sir has been associated with a lot of funded research projects sponsored by various public sectors. To mention few are ISRO, Defense Terrain Research Lab, Ministry of Environment, Forest and Climate Change. Sir has also trained and mastered over 20,000 students as an NPTEL coordinator. Being in civil engineering domain, we all feel truly honored and blessed to be a part of this session. Thank you, sir. Thank you so much. I request you to take over the session, sir.
Thanks to Dr. Arjun and Dr. Lima Rose giving a opportunity to introduce myself to this audience, which is almost 100 participants are there. It's a great pleasure for me to deliver these lectures. Since I just got it that many are most of the students who are attending it, so just they have crossed first years, they are the second years, okay, and this is the batch of this millennium of this century, which has a lot of issues as now if you look at it, come it, okay. So looking the COVID-19 and all the issues, what is coming it, looking this and the fluid mechanics, what should we evolve it, and already I said it that fluid mechanics, the NPTEL course is there, and still the registrations are there. You can just register the NPTEL fluid mechanics course. From that course I'm teaching, I just today discussing with you, okay. I'll start discussing that what are the actually challenging problems. As introduced by Dr. Lima Rose, that I had a 5-year experience in Indian Space Research Organization, ISRO. I know that what are the issues, the challenges are comes in the basically in the fluid mechanics. So let me, I start it with a very good note. I'll just talk about first 25 minutes, okay, and I'll just need your feedback or things that how you can interact me another 20 minutes, then again followed by the another 25 minutes. We can have a discussing about the how the in this present era the fluid mechanics, what context of Reynolds Transport Theorems and all. I'll discuss it, but let us first look at the title. Title is the Aerodynamics of Beautiful Game, okay, with the football. Okay, it is done by one of the MIT professors. These studies, I will talk about that. More details I'll talk about. If you look at the fluid mechanics applications, it's everywhere. Okay, you talk about natural flow systems. Okay, you know it in natural cloud formations, the transporting of the monsoons, rain, all are the fluid mechanics problems. The industrial pipe systems, the automobile sectors, the aircraft, spacecraft. So if you look at the technologies are changing it, and we are making more efficient cars, aircraft, the spacecraft. Also, we have a very limited knowledge, which last 2 years we are really, COVID-19 had saying that the era where we are not discussing much about how the flow systems happens, it, how the blood moves, it, how the concept of oxygen contents, okay, which we today's world we everybody know about SPOT, O2, that means saturation oxygen content, which is so if you look at that, our knowledge is very limited for the how the fluid flow is happens it in terms of blood, in terms of oxygens inside our human body, which is really a lot of things can be done it. You talk about power plant, you talk about boats, ships, and as I'm delivering the lectures in the students on Tamil Nadu and all, if you look at the wind turbines are really going to generate a huge energy, renewable energy for us. How it is possible now to harvest the wind energy, run the turbines, and put it the energy in the gridded networks, and this is what all the possibles because our very in-depth fluid mechanics knowledge. So let me I talk about anyway. So aerodynamics of beautiful game. That's what is a very good the presentations by one of the MIT professors. I'll talk about that. Before that, I'll talk about how the fluid mechanics has really helped us our day-to-day life, as well as all these systems what we are talking today. We are interfacing it. It has the basic concept of the fluid mechanics, starting from natural flows, pipe systems, cars, aircraft, spacecraft, human body, power plant, boat and ships, and the wind turbines. So basically, if you look at that renewable energy, whatever today we have a quite efficient to do the wind energy harvesters. That's because of this well design of this the turbine blades. That's what we design it, and the students who have seen this wind mills, okay, they can see that how precisely it has designed this wind blade. If you look at the fluid mechanics applications, we have a very day-to-day applications we have, starting from automobiles, spacecraft, aircraft, human bodies, wind turbines. You can see that a lot of applications we have a day-to-day life. The fluid mechanics has evolved almost 250 years. If you look at the first equations proposed by Bernoulli, the Bernoulli equations, everybody knows it. This is about 250 years back. So the fluid mechanics has evolved 250 years. Today we have a lot of tools with us. That is the reasons we are making very efficient systems. Like for example, if you look at one of the examples, if you can see that we used to have a arrow, okay, which may be just after our civilizations. The top speed was 300 kilometer per hour. The flow Mach number is 0.3. Today we just move from 321 kilometer per hour to have the spacecraft. The Blackbird, the aircraft, which is moving with a speed of 3,660 kilometer per hour, almost 10 times. The flow Mach numbers is a 3.35. That means this aircraft is moving 3 times faster than the speed of the sound. So we have really achieved the speed vehicles like the aircraft of Blackbirds, which is moving with a speed of, design speed is, top speed is 3,600 kilometer per hour. The Mach numbers, which talks about speed of the vehicle by the speed of the sound, is a 3.35, 3 times higher. The same way, Rafale, you just have this. It moves a speed of, top speed is about 2,000 kilometer per hour. So we are moving with a very high speeds, high Reynolds numbers, and we are also moving it to the high Mach numbers. That is what, though it's a moving, like Rafales moves at 2 times speed of the sound. That's what is the speed of the Rafales. So if you look at that, the technology has evolved to make it this aircraft, which is today's, I think that is what the assets, that is what the technology has improved it. Also the fluid mechanics applications has improved it. And that's the reason if you look at the bullet train, if you go to Japan and any other places like China, so that trains are moving at speed of 400 kilometer per hour, 500 kilometer per hour. So these aerodynamic studies, it was done very precisely, and technology for that type of things also developed, which is making us to move so faster than the speed of the sound. Now, if you look at, go back, okay, big portions is, we know it, okay. If you look at that, we talk about the Bernoulli equations. See, in the Bernoulli equations, okay, which many of could have learned it in the class 1 or class 2 levels. But this Bernoulli equations talks about very simple fundamental of energy conservations. And that energy conservation equations of simple Bernoulli equations we can use for many places. Like, for example, I just want to know it, okay, if I have a blood band, I try to measure the pressures at the 2 points. If I know the velocities, I can compute what could be the velocity flow through this blood fan. That's what we can measure it. Following very basic concept. We measure the blood pressures, okay. So often we measure the blood pressures. So based on the blood pressures, we can measure it, what should be the velocity of the blood fan, through the blood fan. We do a lot of other approximations. Same way, if you look at the air cup concept, what we have is airfoils. So as you know it, when a flow go through these airfoils, so what will happen is your in the top and down, okay. So you will have the lifting of air when it happens. That is what the drag force or lift fits works it. How to design these airfoils? That's what we did a lot of study to design the wing, the shape of the wings. That's what we have designed it. Same way, if you look at that, many of the times of the coastal area when you construct the house. So whenever you have a cyclones, then we have a major problem of the blowing of these houses. That because of simple Bernoulli equations, you can understand it, how the pressure difference matters it, and because of the pressure difference, then it just lift up. That's what is additional pressure force works on That is the reasons the roof will be blown away from this thing. That the way, if you look at the simple, the house constructions, the biological things, and the aerodynamic things, which is very simple Bernoulli's equations, a way back to establish between the relations between the speed and the pressures. Now, if you look at our sense of balance, okay, if you look at that more details and biological part, which is a really interesting part, okay, and that part, if I try to look it, is it my screen is visible now?
Yes, sir. Yes, sir.
Okay. So if you look at it, I'm not going details, okay. How do we hear it, okay? So our ear is a sensory organs, uses the sound waves, allow us to hear it. But if you look at the air travels within our ear systems, that itself will tell it how natural systems are built up. Okay, I'm not going details, that our sense of balance of organs found inside the inner ear. So you can try to understand that fluid mechanics in terms of airflow, the water flow. We can try to understand our biological systems. Okay, and if you have any sort of the problems with these natural biological systems, you know it, how things are goes out of order for us. Same way, if I go for very simple things, that story of Wright brothers flight, which is there in my NPTEL lectures. The students, we can go for NPTEL lectures, which is there in YouTube also. You can have a YouTube lectures are available there, and you can see it. Today, what we have, accessibility or the power to travel from X locations to Y locations. That's what is because of the contributions of these two brothers, the Wright brothers. Okay, so almost 120 years back. Okay, almost 120 years back, they try to mimicry very simple things that of the bird, same things they want to mimicry to create the concept of. Can you hear me?
Yes, sir. Yes, sir.
Okay. So they try to mimicry. Just if you look at this part, okay. So how to wings should be, and that's what is the fluid mechanics problems. That's what is, if you can try, it is a fluid mechanics problems. That's what they try to mimic it, and based on that they make a flyer clocks, and they try to lot of innovations. They tried it to follow closely bird's wing balance, control, and successfully develop wing graphing. And that wing graphing help us. That's what it help us to make it now these the aircrafts. Okay, there are a lot of failures. Okay, it's not that only a few days they are able to do it. There are a lot of failures, a lot of. By the end of the day, they have success now. That is the reasons we have now the aircraft industries. Okay, airplanes are there. That's because of Wright brothers. Okay, two brothers, they have made it this successful story. Another problems what we look at. Okay, if you if you look at that, we in our country, or if you look at the World War II, there are a lot of aircrafts are crashes in the Eastern Himalaya. Okay, so why did it happens it? This itself is a fluid mechanics problems. Because, for example, if you talk about the Himalayas, we talk about the Western Ghats, when you have the high altitudes, your atmospheric condition changes very fast. That means it changes the pressure field, it changes the velocity field, it changes the aerodynamic conditions of around the helicopters or any space aircrafts. So because of that, there are a lot of macro turbulent structures also formations happening. And that is the reasons you see that many of the times we have a crashings of the helicopters, the army helicopters, and many helicopters, even if in case of the World War II, Many they lost their aircrafts when passing through this eastern Himalaya. So if you look at what I'm talking about, our understanding of the fluid mechanics still it's not in that level. We understood some components, we developed the helicopters, how to have what should be the speed, what will be the lift force, what will be the drag force, but still we are not understanding it when interacting with a extreme conditions of cloud burst, extreme conditions of pressures and the velocity field, even if we have the aircraft helicopter crash. So that we should try to understand it. It has a lot of applications, not only to design the helicopters, also how this efficiency of the helicopter flying we can improve for a different terrain conditions. That's a bigger issue. Today we have bigger issue that how we can design the aircraft helicopters so that it can, even if high altitudes with a macro turbulent structures, it can able to land it properly. This is biggest issue now. So same way, if you look at the fluid mechanics, what is helping us, and we have given the examples. If you look at in a NPTEL platforms, you look at the natural conditions, and you look at these videos, okay, which is so it's very. What is the strength of aerodynamics? Okay, a boss, okay, which we don't believe it can roll like that, okay. A bus can roll down it. That is the photograph of last year's. Okay, so if you can see that bus is rolling down it. The same concept we have done it for a wind tunnel. Just to look at the wind tunnel. Just a look at the wind tunnels. Also, we can do the similar studies. We can try to understand it, how the pressure fields are happening it, how the velocity fields are happening it, how these making this bus in a rolling stage. Same way, if you look at, we all know about the super cyclones. Okay, many name of the cyclones we are talking about. And if you just observe it, how the cyclone is propagating, what is the velocity field, how much soil moisture containing it, all today we can solve it. And that's what we are demonstrating. You see that one problem is a smaller scale problems. We're talking about ruling of a bus, or we are talking about the cyclone formations in the Bay of Bengals, traveling 2 or 3 days, accumulating the soil moistures, the strength of the vortex are changing its cyclonic vortex, and how it is moving it. So all these are possible today because we have the fluid mechanics knowledge or in terms of computational fluid dynamics. Now, let me I come back to the beautiful game, which is a football. Okay, so if you look at this, this is very interesting photographs. How the ball spins it. Okay, so if you start the spinning the balls, okay, then it start the Magnus effect. That means it's try to move in the lateral directions. Try to move in the lateral directions. Because of that, very nice way this ball makes it the goal post. That's what this is full of the knowledge of aerodynamics, knowledge of what type of balls are there, how he's kicking this ball and start the spinning and creating this Magnus effect, back spinning, side spinning, then it's like a ball falls like this. Okay, so if you look at the projectiles, you look at the projectiles, how it is happening. So these Magnus effects, if you look at more details, I think my friends who are really good in the footballs, they can know it, this Brazilian free kick, okay, which change our fluid dynamics. Many of the professors in developed country, they try to understand this fluid flow, how it could be happening. Okay, so if you look at this kicking, that they try to do the similar things in the wind tunnels and target it, how can happen this, the reverse Magnus effects. Okay, reverse the Magnus effect, which makes the process will be the not a lifting, also the going down, that process can be doing it. If you look at the photographs and if you look at this wind tunnel test, that's what I'm taking a source of MIT lectures. And if you look at this way, it's quite interesting. And you can understand it, one penalty shot of these things can change the life. So precise practice by the football players, aerodynamic conditions, the conditions of the balls, makes it a so precise kicking. That's what is 97 goal. That's what studied by many peoples. And we brought a new concept of reverse Magnus effect. Now, if you look at the size of the footballs, okay, color of the footballs and the roughness of the footballs, the material of the footballs, that's what is changing it, because that's all these fluid dynamics, okay. All these fluid dynamics, the materials, all it's a changing it. Why I'm talking about the football? Because this is the match we really invest a lot of money, because one of the free kick can win a match, and you know it, how much money is involved in Euros, okay, playing a match. One goal can make a hero. So if you look at that way, they do very extensive studies at wind tunnel level, materials, the stitching. They do the computational fluid dynamics, try to understand it, how to improve the trajectory, the ball games in such a way that they can make a best balls, okay. And I just want to show you I'm not going details because we had started a bit late. If you look at that, if a ball, you just kick it, this is what we know from the class 11 and 12, without any drag force, I'll have a symmetric projectile. The ballistic will have a symmetric thing. And because of the drag force, the things of what happens, it is like this. I'm audible?
Yes, sir.
So if you look at that, that's what the same balls, because of this drag force, your profiles are changing it. These profiles are changing it for different atmospheric conditions. And that's what comes is a drag crisis. It's a very simple example. It's a very simple example. They are showing it how we can have the trajectories, okay, how we can have a trajectory, and as you have a drag force, you have this part. Why we are getting so much drag force? Now we need to understand these very minute levels. I'm not going into much details, but there are the equations is there. We can solve it. I'll show you some of the slides that if you look at what is actually happens, just look at these figures. Just try to understand these figures, which talks about with a different Reynolds numbers. Okay, different Reynolds numbers, how these flow structures changes it. Just this is what the study was done almost 100 years back. To understand it, even if you have a sphere, you have a uniform stream flow, how the structures are changing it, if we had to change the Reynolds numbers. The first one is the Reynolds number less than, very less than 1. That means maybe a conditions where small virus is just traveling through a very small velocity of the flow. As you increase the Reynolds numbers, go up to 200, 210 to the 2 lakhs, okay, then you have a different type of process. There is a flow separations, there will be the turbulent structures, the vortices formations and all. So if you look at just changing the flow Reynolds numbers, which is a relationship between ratio between inertia forces and viscous force, the flow structure changes it. As the flow structure changes it, it have a viscous drag, also the pressure difference drag will be there. Your drag components also changes it. That is the reasons if you look at that, the spinners, okay, in cricket we know it, the spinner bowlers, okay, sometimes it works it, sometimes doesn't work it. If you just hear any commentary of a cricket match, sometimes the spinner bowler, they do very marvelous job to spin the ball, but some other evening also they cannot do well, because this depends upon atmospheric conditions, the pitch conditions, and how the bowlers are understanding it, at what could be the Reynolds numbers you will throw it, and what will be he induce the spin such a way that you can have the spinner the ball trajectory which will be confused to the batsmen. So if you look at that, this is basically the fluid mechanics. Detailed understanding of the fluid mechanics can tell us why it is happening. Whether understanding that, can you make it a new way of the bowlers or our batsmen, they can understand the thing. Or nowadays we call it the simulators. Okay, that's what it happening. Okay, when you go to play any game, you do a simulators. Okay, you just simulated the things. That's the same concept. It's follow it. You try to follow the fluid mechanics, the Navier-Stokes equation solvers. When you throw a balls in a simulators, mathematical simulators, the games are there. What it does, it does the solutions of the Navier-Stokes equations and try to get it how much spinning will happen, it how much the force will happen, what will be the trajectory. That's what will be possible. That's what is the all your computer game animations, they consider in the backbone the fluid mechanics solutions that the Navier-Stokes equations solve. Now in the last year student my batch, we try to introduce that whether we can use ANSYS Fluent, which is free software, and I can advise to students to today is actually we have a strength. We can use very sophisticated commercial softwares now. Today is free, so you can use the ANSYS Fluent instead of playing another computer games. You can use the Fluent software or any other computational fluid dynamic softwares to learn it, how the pressure velocity are changing, how the turbulence structures happens, how the vortex formations happens. If you look at it, this is what F-16 fighter jet did by the last year's IIT students, because they cannot come to the campus. Okay, everything's is online. So we try to do the same using this ANSYS Fluent. We try to simulate this. You see this F-16 fighter plane, which is having a speed of 410 meter per hour to 840. Mach number is 2.45, and we have an incompressible flow and pressure bed solver. I'm not going into the turbulence structures and all. See, this is what is possible now. You can see the streamlines. You can see this how those pressure difference are there. So complicated things, and that's what can be possible today. It's not a big issue. So with this, ending my first lectures. If you have any questions, please ask me. Yes, please.
Sir, my name is Mohan Raj, sir.
Okay.
I have one question with respect to application in fluid mechanics. Sir.
Yes.
We use wind turbines in areas where we have a specific speed of wind. But why
Yes.
not used it in coastal zone areas, sir? Why is it not so familiar in coastal zone areas?
See,
is there any specific with respect to fluid mechanics, sir?
Okay. If you look at the wind turbine, basically it needs to have a particular directions. The wind should flow is there, and they have also automatic system. They can orientate their turbine, their blade, so that they can get it the efficient energy for that. So that is the reason the site conditions are very critical, where they can actually install the wind turbines to get the energy. The wind, they do this the wind analysis, because they try to measure the wind direction, wind velocity, daytime, the evening times, what is the, and based on that they design the wind blade and turbines. All they design. The problems comes it two ways, that some of the locations maybe they are maybe having a high velocity of the wind, okay, like coastal regions. If it's a fluctuating lot, also that is not good for them. And we are doing well in a wind energy harvesting. We are doing well. If you go to in developed country like Europe, everywhere you can see these wind turbines. Only the technology is taking time to come to our country, but we'll succeed. We'll succeed to have a wind turbines in many places in our country.
Thank you, sir. Thank you.
So, myself Mageshwari sir,
Yes.
Assistant Professor, Civil Engineering. Sir,
Yes.
I had a question that, so generally we are always talking about the fluid flow and all, but
Yes.
is there any software, otherwise any other technique to find out the blockages in the pipeline or a sewer line like that, sir?
Oh, no. Okay. I was talking about these softwares because today is a free, many commercial softwares are there. Okay.
Sir,
If you look at that, and many free open platform softwares nowadays, CFD softwares are there. Okay. That is what it happened in last 10 years. The open form, the softwares are also much robust than the commercial softwares. Okay. And there are the groups and all. That is not a big issue to get a CFD softwares. As you talking about pipe blockage, I will tell you it's a very easy to identify. See, if there is a pipe blockage, there will be a pressure difference will come. And to measure the pressure difference, we have a lot of devices with us. We can easily identify it. See, if I have a blockage, any degree of the blockage we have, if I measure the pressure difference, that's can give me the monitor the pressure difference. I can get it that there is a blockage has started. And there are other devices nowadays coming. Basic concept is that same. If you are reducing this flow area, your velocity will increases, the pressure will drop it. That's very basic concept. Yes, any other questions? Yes, any other questions? Yes. What I'm suggesting the students, if you see, whenever you play any computer games, did you understand it? What is the backend things are going on? These are all fluid mechanics, the basic equation solvers. Like when you increase the speed of a car, you can see that more drag force you are feeling it. That all the concept they have brought it from the fluid mechanics. They make it as natural you are driving a car. How it is happening it? In a back end, you are feeling it that they are using the basic fluid mechanics equations, which are Navier-Stokes equations. From there, they computing the drag force, and that what you are giving to use your computer games. You make a speed of your car 200 km/h. The projectile motions of your car will be different. If you move it 50 km/h, your projectile motions will be different. Daytime, evening time, the drag force will be different. That is the way they are making you to edge, natural edge to feel it. But end of the back end, what they are doing it, they are solving the Navier-Stokes equations. try to find this velocity distribution, the pressure distribution, drag force, and based on that, it's making a projectiles. That's the reason you feel as natural as you are driving a car. So many of the computer animations, what you are looking at, the back end is the fluid mechanics solvers. That's what my hints to you, okay, who are students are watching me. Whenever you play the game, just think it that the game, why it is so natural? Because they follow the fluid mechanics principles. I'll just discuss
Yes, I can see, sir.
very basic things which we generally don't cover in our fluid mechanics undergraduate levels, which is called the Reynolds Transport Theorem. I think that is the reason our students are not fascinated to read our course, which we treated the fluid mechanics as individual chapters, like fluid at the rest, fluid in kinematics, fluid in dynamics. We make it separately. And the students just know it, everything's are separate. Okay. So mass conservation equation, linear momentum equations, energy conservation equation. And most of the times when you ask the students, what is a Bernoulli's equation? They know the Bernoulli's equation expressions, but they don't know what are the assumptions behind that. How is it a energy equations or is it a linear momentum equation? All it's a confuse to them because we have not integrated them. Most of the books which follow in our undergraduate level, I don't want to tell the author names. Okay, you know it. They have made it more towards the problems solving attitudes, which is for maybe a GATE, maybe engineering service. So they are trying to write these books which is just for a problem solving attitude, not to give a conceptual understanding of the fluid mechanics. The beauty of the conceptual understanding of the fluid mechanics help us to solve the real life problems. Like for example, you can use the Bernoulli's equation to get the pressure and velocity, but when you go for higher Reynolds numbers, or I have seen it the F-16 fighter planes, you can just think it where you have to apply the Bernoulli's equations. Where I will get the velocity. There are a lot of vortexes are happening. There are a lot of turbulent structures happening. How can you do that? So if you look at that, there is a gap, a large gap between whatever is there, the approved AICT syllabus and present era, the demanding era. Demanding era is different. At present, the fluid mechanics knowledge what you should have, there is no partitioning. That's what is there. The basic gap, I have seen it. There is a two very good book which is there in NPTEL. If you can look it, many of the times we cross-refer it. One of the books is Sindel Simbala, and another is book is FM White. So please look these international books, which is nowadays there is a Indian editions of that. You look at their illustrations, which is a very fantastic illustrations are there. They don't confine it just for Bernoulli's equation. Even if they derive the Bernoulli's equations, they given a full spectrum of Reynolds Transport Theorem, how they can integrate all these things in a one platform. That's what the Reynolds Transport Theorem. I'll not go much details. I'll talk about, okay, how do you solve this equation? Everybody knows we have empowered with the three laws, the three physics laws: conservation of mass, conservation of momentum, either linear or angular momentum, conservation of energy. These things we know it. Okay, very basic equations we know. But these equations is valid at the system level. Valid at the system level. All these mass conservation equations, whatever we have, we just try to look it and it works fine when you talk about the system level. But when you talk about the control volume level, many of the times we follow a control volume concept in the fluid mechanics. That means we define the area which is our area of interest. Define this area which is our common interest. And that area we try to look at the average properties. Okay, we are not bothering beyond within the area, but I know the inflow, I know the outflow. Then I try to do mass conservation equations, the linear momentum equations, or energy conservation equations. More detailed derivations are there, and I spent the Reynolds Transport Theorems. If you look at my YouTube, almost 3 lectures I am talking about that. Because that understanding we should have, and if you look at when you, I'm not going to derive part. What is the systems or the control mass? It's focused on the set of the fluid particles. Okay, that's what is the systems. We talk about a set of the fluid particles and we track about that. Where in the control volume we focus on a region of space where I'm interested. Okay, so that's the reasons it confined by the control surface. So I'm not talking about fluid particles because I am not, when I'm addressing the control volumes, I'm not considering in the system set of the fluid particles. I'm considering this is my control volume. Okay, how much of mass flux is coming in or going out. There is no mass flux changes here. Here, what is the momentum flux? What is the momentum flux is going out? How much of energy comes in because fluid is coming and going out. All the things, it happens through this control surface. So now all these basic equations, what we know it at the system level, because we have a mass conservation equations, we have a linear momentum equations, and the basic equations what we have, this energy conservation equation, all at the control mass level or the system level. But in the fluid mechanics, we mostly follow this control volume approach. Now this control volume can have 3 types. Control volume can have a fixed control volume, can have a movable control volume, like you can consider a ship is moving with the velocity v. The reason behind that, which is moving control volume, okay, which is moving control volume. Or you can have a deformable control. Okay, please don't be, the control volume what we consider, it doesn't mean that these control volumes will be the fixed. It can have a movable control volume. It can have a deformable control volume. So I try to write the Reynolds Transport Theorems, establish the relationship between system for the basic equations from system level to the control volume. Then it's a very easy to apply the control volume. The control volume can be as big as the Earth, as small as a nano level also. Its control volume can be any shape, any size. It can have a movable, it can have a deformable, it can be the fixed kind. So the control volume, the concept we should understand it. Because if I know exactly how to apply the control volume, then I can solve the problems. It's not related to civil engineering. I can solve the problems in chemical engineering. I can solve the problems in mechanical engineering. So there is no difference. Hydrology or all the field, but everywhere we are using the control volume of different size. Either the control volumes at the fixed, movable, or the deformable control volumes. Okay, more derivations I'm not going it because we don't have much time. Okay, so I'll be student. I want to encourage it that I know it. The control volume equations, when we derive it, finally looks at Reynolds Transport Theorems is too difficult equations. Okay, because it has a surface integral, the volume integrals, it has time derivatives and all. but it's a very simple concept. You just try to derive it. It looks a very difficult. There are the surface integral. There is a, but when you really focus it, if you look at it, it's just doing the balancing. Okay, the summation. So if you look at that, it's try to consider it that velocity variations, the moment mass flux variations and all. That's the reason it looks a very complicated. But these equations, if I very strategically write, it will come. It's very basic equations. We know it. Q is equal to and B. So from this equation, which is looks a very complicated equations, for mass conservations, I can write it Q is equal to AB. It looks a very difficult. That's what I'm encouraging you. But if you do a simplifications, finally you know from class and 12th level, QE is equal to A and B. That's what is the mass conservation equations with. There is a series of approximations. So this is the basic equation. If I do the approximations, I'll get Q equal to A and B. Then you can always ask me questions, sir, if this is Q is equal to A and B, why should you need a so complicated equation? I'll tell you, 150 years back, we have the problem to solve with Q is equal to A and B. Today problems, what we are solving it, we cannot solve with a Q equal to A and B. We have to take care of many things. Many processes we're trying to take care of. That's what can possible if you go for basic equations, which may look a bit difficult, but that is a way to solve it, because the era of Q into AV and the Bernoulli's equations, which is 150 years old equations, it doesn't help us now, unless there is very specific conditions. Okay, so that's my point. I'm not going more details here, and because anyway we are a bit delay. There are a lot of mathematics I told in my class in YouTube, but I tried my level best to explain each terms, explaining each terms, how it is linked each others, how we can consider the control volume. Whenever we solve these problems, we first should sketch the control volume and the control surface. If you do it, like for examples, I'll show it. Whenever I'm doing this type of experiments, okay, so we can choose a control volume. Then I find out where the mass flux is coming, where is the mass flux going out, what are the forces acting, because of gravity force, what is the hydrostatic pressures, and all these things you can equate. You define the control volumes, and then you try to look at how the mass flux is coming in, going out, momentum flux coming in, going out, the rate of change of the momentum flux, which will be generate the force on this state. So when you solve these problems, please have a practice to sketch the control volume. Please, because if you really sketch the control volume like three-body diagrams in a solid mechanics, it will give a lot of energy you to understand the flow problems. Otherwise, if you look at a Q1 is equal to Q2, I think it doesn't inspire anything to us. Because, for example, do you believe it that when you have a pipe flow, the velocity is a constant, is uniform? No. In a real pipe flow, we cannot have a uniform conditions. So how will you get the velocity V? I cannot get a velocity V. No doubt academic problems, as I said it, many of Indian textbook, they just give the value, you put a Q1 and Q2, you solve it. That's what is academic problems. But if you look at the real life problems in a pipe flow, I cannot have a uniform velocity. The velocity doesn't change it within the cross section. That cannot be possible. I cannot make a pipe where the velocity is uniform. But if you look at it that way, but in our academic problems, we put it in your any textbooks. we put it, the velocity is uniform, and then you solve the problems. So that is the reasons my point that please students, I know it, I'm a bit far away from you in these online classes, just to think it, the concept of the control volume, which is very, very nicely represented like a book like Sinzel Simbala, FM White Fluid Mechanics book. Just read. Even if you don't read the fluid mechanics book, I just encourage you, you have enough time to just see the illustrations, how good illustrations they have given it, how good the real challenging of the fluid mechanics problem also they are discussing. How to solve the problems not remembering this Q1 and equal to Q2. You need not to remember it. Your conceptual understanding can help us to solve the problems. You need not to mug out your Bernoulli's equations, your Euler equations, or your pipe flow equations and all. You just have a conceptual understanding how we can solve these problems. I think that's what is a major problems, and that's what we also solve the same way. If you look at the pressure drags, conservation of momentums, we have given a lot of examples. The same slide, I mean, whatever there in YouTube and NPTEL, same things are here. How we are using the conservations of momentum, and we are discussing about momentum flux correction factors and linear momentum equations, the control volumes, control surface. If you look at that, we have a steady flow with one inlet, one outlet, which is very easy. But if you have a different conditions, you simplified it, how you are solving it. I think I don't have to put much more time, and I'm there in YouTube. I'm also there in SWAM platforms. These coming semesters, I'll be there. So, and I have a group of students who really work hard to prepare all these PPTs points, and so that way, can you have any questions on these, that why we need Reynolds Transport Theorems, or what type of questions comes from in a gate engineering service, and what way you should prepare it. You can ask me some questions unrelated to gate engineering service and how to score good marks in related to fluid mechanics, or same way. If you have a knowledge on fluid mechanics, you can do well in hydrology, you can do in knowledge in a good in hydraulics. Any questions? Or any suggestion on the fluid mechanics? If you have taken the course last year, the NPTEL course, then you can give us some suggestions. Okay, some suggestions always. Give us some suggestions that we can improve it with time. I'm audible.
Good afternoon, sir. I'm Arun Raj.
Yes.
Sir, can you explain the concept of flow separation and cavitation, sir? What is the difference between the flow separation and cavitation, sir?
Okay. Okay. See, if you look at the flow separations, comes from the no-slip boundary conditions. The fluid has a inherent properties, like we know, the human beings. Okay. Like we always try to move with what is our neighborhood speed, no? Okay, if you look at that, that is a human nature. The fluid also behave like a human behavior. That if a fluid passing through a solid surface, okay, it has to have a fluid particles will be the speed of the surface. That means if the solid surface in a fixed conditions, the velocity at that point of the fluid particles will be tending to the 0. If that plate is moved or the fixed surface is moving at the velocity v, then you will have the velocity also, the fluid particle attached to that will be moving with a velocity v. So these are conditions is called a no slip condition. But what actually happen is talking to the flow separation. When a flow passed in a cylinders, as the flow passed toward the cylinders, then it starts a formations of the boundary layers. And when you go to turbulence boundary layers, beyond that, it creates a pressure gradient such a way that the fluid particles doesn't keep it touch over this boundary. It goes out. As it goes out, that flow separations happens. Because fluid particle doesn't keep it touch over that. Because there is a negative pressure gradient creates it. Because of negative pressure gradient, fluid particle detaches from the surface. So the non-slip boundary condition violate there, and it creates a separation zone. That's the big, there is no problem. So having the separation zones and the turbulence behavior flow past in a cylinders or the spherical objects, we can see that flow separations happening, the boundary layer formations are happening. But if you talk about like a turbine, we have a hydropower and we have the turbines. When you have the hydropowers, like for examples, okay, Hirakudu Dam projects and all, which is about, so we change the potential energy to kinetic energy. The huge increase of the kinetic energy, we do it. We bring through the penstokes, we bring these waters, we convert from the potential energy to kinetic energy. As we change the kinetic energy and goes through this turbine, because of that, the very high velocity pressure drops. When the pressure drops below a vapor pressure, then what it actually happens, the liquid waters convert to the vapor. They create a bubbles. Near the turbines, it's created bubbles because the liquid waters phases to the air phase and create the bubbles. And that the process is the cavitation process. So the flow separation is different, which is the boundary layer concept, but because of the pressure drops below these vapor pressures, liquid phase of the water convert to the air, it creates the cavitation process. And these bubbles, what it's created, when you transmit it, it dissipated high energy. That's the reasons we have the eroding the turbines and all the things. So we try to avoid the cavitation process. Is it okay?
Yeah, fine, sir. Very fine. Exactly, sir.
Sir, this is Satyanarayana Sharma, sir. Sir,
Yes.
We have agriculture students participating in this event, sir. Nearly 50 plus students are there. So I request you to
Yes.
give some insights on agriculture field, fluid mechanics application on agriculture field, how it can be relevant.
Okay.
Some insights on that.
See, I do believe it in, because I do some research related to agriculture. If you look at how the water flow process happen within the plant, it's a very complex process. How we are making a drought resistance crop. So that understanding, see the photosynthesis process, how the water is taken by this plant, and how the crop, the agriculture respond with a different degree of the temperatures, the evapotranspirations process, all we know at the gross level. I have a very beginning when I was there in ISRO, I was working with the agriculture area. Evapotranspirations, we just don't bother about much. There you need to have a fluid mechanics knowledge. Without fluid mechanics knowledge, you will say that it's an average process. This much of of water, it evaporates. Why does it evaporate? What is the controlling factors? How the aerodynamic conditions are prevailing it? All you have to understand it, how the soil moisture behaviors are changing it. If you have a understand, like I have shown you these Reynolds Transport Theorems for a control valve. The same way, when you estimate the soil moisture variability, we also use the control valve. But it's a porous media with a soil structure. That's so different. Only that is a different. Here I consider it porous media. But when you analyze same mass conservations, the energy conservations, talking about linear momentum, we simplified it, but we also look at the same concept. What is the Darcy's equation? It's a momentum equation. So it's a gross momentum equation. So what is the idea we have in a fluid mechanics? At the different scale, we do a different approach method. The students, if you want to try to understand more in depth at the microscopic scale, they have to understand the fluid mechanics well. Really, and I believe it is more challenge in agriculture as compared to the water resources or civil engineers. Okay, civil engineers anyway. There are many technologies are there, but agriculture engineering students, they should understand much more detail of the fluid mechanics.
Thank you, sir.
It's that is the, they can innovate it. They can innovate it many things if they have the fluid mechanics now.
Yes, sir.
Sir, I have
They
one more
can
doubt, sir.
Yes.
Sir, because the fluid flow measurement for using the pipe flow problem, the flow measurement device for venturimeter and orifice meter will be used, sir. So what is the difference for rotometer, sir? Why we are using for rotometer? Some cases they will be using for rotometer.
See, if you look at these venturimeters, okay, it have the very basic concept which is 250 years back. Okay, venturimeters we have not innovated now. Okay, it is much. I think the era we never saw the aircrafts. No, the venturimeter. If you look at the venturimeters and all, it's maybe something like 500 years back. People know it. If they restricted the area in open channel flow, they will higher the velocity, and if they make it a critical depth, and they can measure the discharge, or they can the same concept they put in a pipe with a venturi to reduce the flow area, the pressure difference will come, and pressure can easily measure it, so you can make it the discharge. But try to understand is that the venturimeters gives a lot of errors, and this error today we cannot afford it. See, today we have a gas pipe connections to your house. Okay, many of the cities coming in. Can you afford to have a measurement 30% error? You cannot have. The company can really wash out. If you have a venturimeter, put it and measure the gas, how much of gas I am using it, my cooking, it can go anything, no? Because it is so erroneous. The earlier we used to do the venturimeter, that's what I am telling it. Okay, what earlier we used to do it, no doubt our fluid mechanics curriculum still talk about venturimeters. Okay, still we use the Bernoulli's equations to solve that, academic problems to solve the get the engineering service. But today what we need a very precise instruments. It is possible. There are a lot of instruments are nowadays coming to precisely measure the discharge. The rotometers is a same concept of the wind turbine. Wind turbine, if your wind velocity is there, it rotates. If you measure the RPM, you can have a relationship with RPM versus velocity. The rotometer does same thing. If you do that, there is a rotations happens. So with a rotations plus, if I know the velocity, a calibration chart, I can always get it. This many rotations, this is the my velocity. So we measure the velocity. If I know the flow area, I can get the discharge. That's all. What my suggestion is that now really technology has evolved in the measurements of velocity, the discharge. A lot of new devices has come in for discharge measurement. We should go out from venturimeters. I'm not having much because 250 years back technology, whether we are using for anything, no. Why we are fixed on the venturimeter? Any questions? It's good. It's okay, na?
Yeah, yes, sir. Yes, sir. Fine, sir. Fine.
Yeah.
Sir, one more basic question, sir. While plotting the velocity distribution, sir.
Yes.
For pipe flow, if you consider for one dimensional, you will get bottom will 0, at the middle you have a maximum velocity. What about other two direction? Generally, fluid is a three-dimensional nature.
Yes. If you look it, okay, I think even if the flow is actually three-dimensional nature. When you have a pipe entrance, you can see that flow will be the three-dimensional nature. Okay. It will have the flow in a three velocity component. But what we look at, that three velocity component, what I'm getting it, are they in the same order? That means if I'm measuring a velocity in terms of 2 meter per second, another is 1.5 meter second, another is 1 meter per second, then all are in the same order. But if I have a velocity, one is a 2 meter per second, another is a 0.2 meter per second, another is 0.00.2 meter per second, then I can neglect that part because that velocity is much lower order than the velocity of the prime field. So basically we do a approximation to simplify the problems. That's some of the cases the velocities of a jet direction or any other direction is not that significant order than the velocity what we are analyzing. So we nullify that. It's a order analysis. Also the flow characteristic analysis, as the flow grow through the same pipe, all these idealistic conditions, then it attends to not a one-dimensional flow, it's a two-dimensional flow, but we make it like you have a pipe flow, it's not really one-dimensional flow. It is longitudinal direction, but it's a radially symmetric will be there. But it's a parabolic set. You can see that this parabolic set, nothing like one-dimensional. What we do it, we consider the average velocity, we consider the momentum correction factors. That's the story we are not telling it. Then we are applying this Bernoulli equation. So we did a lot of approximations.
Thank you, sir.
That's what we do.
Thank you, sir. Thank you, sir. Sir, last small doubt, sir, regarding the fluid mechanics project, sir. Sir, because in our curriculum we have a design project will be, sir, the final semester. Most of the civil engineers they chosen for the analysis and design of RCC building or steel building. They did not go upon the steel project. Give some input about the project related to fluid mechanics, sir.
That is what I'm telling it. I'm just giving you suggestion. The Fluent like a software which is a free, which is a very costly software. Today in this COVID-19 pandemic period, they made it free. Please do some experiment using this Fluent type of softwares. Then student will be really interested. Really, they get it. What is the flavor of the fluid mechanics?
Yes, sir.
Why it is a problem with the fluid mechanics? Even if I'm really glad there is 100 students anyway hearing me, may not be interacting me.
Yeah.
See, the problem is that the fluid mechanics problems which is coming today and what we have in the lab, there is a large contrast. Today there is a pollutions problems, air pollutions problems. There are the problems because of turbulence behaviors and all. To represent that, we don't have a good lab facility. So we need to go for a Fluent type of software. Let the student use it, at least virtually feel it, how complex, how beautiful fluid mechanics. As a teacher, I believe it, we are not giving them to scope to really understand the fluid mechanics, which is complex in a mathematically. Many of the book made it complex, but because of availability of these softwares, now the student can really do a lot of parametric studies and can look at how it happens. Like you can give a different, very beautiful projects you can give it, which they can really remember there in throughout lives, that using the a CFD software, they can solve it. And they can see there are a lot of visualization softwares are there. They can see it, like as is showing it, the F-16 fighter plane. You can give it for different type of racing cars. Let them simulate it. Let them see what is happening. How this multi-phase flow is happening. What my suggestions to or my this encourage the students, please go beyond. I know it. You have to follow the textbooks. Okay, today challenges are in a different levels, and if we believe or if we dream of to be a world leaders, I think we should not limit ourselves to the Bernoulli's equation, which is a 250 years back. I'm talking the people who will be the world leaders. If we have dreamt of that, I think we cannot use the Bernoulli's equations to be a world leaders. We cannot. We cannot be a world leader by 2050 by solving the Bernoulli's equations, because that's what it's. You look at the China, how it is doing it, how they are using the curriculums, how they are modifying the curriculums, how they are took these problems in the undergraduate levels. I know it. I cannot change the AICT. I cannot change the course curriculums. Okay, I can talk to you only.
Thank you, sir.
Sir, am I audible?
Yes, ma'am.
Yes, you are.
Sir,
Yes, ma'am. Audible, ma'am.
Yes,
sir,
Yes, student. You have any
Sir,
query?
yes, sir.
Yeah,
Sir, there is a recent trend going on the vegetable dynamics, sir. Can you tell me anything about this vegetable dynamics, which has related to the plants and the root shoot movement, which is most accurately related to the fluids suction and absorption, sir, and how it affects the plant's growth and maturity rate, sir. So, can you
I
tell
am
me
not
about the
getting your
vegetable
questions
dynamics?
perfectly.
Yes, sir.
See, that's what I said it. Okay. I'm not in this agriculture field, but I'll tell it. See, you try to understand it. Not only the fluid flow. If you talk about heat transfer, also the same concept. Heat gradient happens it from the higher temperature to lower temperature. So if you look at the heat flow, the fluid flow, all are the same concept, same Reynolds transport equations and all. The mass balance, the heat balancing, we are doing it. So my idea, what I'm telling is that whatever your problems, you have to simplify it. If you look at, as I did it, a forest ecology studies, I was observing that forests are much smarter in terms of river, in terms of water efficiency. They know how to store the water for the drought. If you see liquid is a big forest covers, even if one or two drought, they don't die it because they have their own storage of this. So if you look at the natural systems, I'll tell you that you have to understand the fluid mechanics. Also, we try to have a conceptual the figure. Conceptually, how this mass energy happening it, energy is happening it, how the photosynthesis process. If you really relate it, it's possible. It's a possible now. It's not that difficult. We are, some of the studies are also going on in natural science. The study has not gone to that level because, as I said it very beginning with the football games, money matters, no. So that's the reasons that a lot of studies have been done in footballs. Okay, how to design a perfect balls with a Magnus effect and all, but we have not studied that details, microscopic levels for the plant process and all. There are a lot of scopes out there.
Okay, sir. Thank you, sir.
yes. I request Nandini ma'am to deliver. Thanks.
Good evening, all. On behalf of Department of Civil Engineering, SRM Valliammai Engineering College, I would like to thank our guest speaker, Dr. Subashisa Dutta, for enlightening us with his knowledge. As Mr. Arunraj Krishnadas sir mentioned in the welcome address, today is undoubtedly a red letter day in the Department of Civil Engineering. Today's lecture was full of knowledge and interesting stuffs. It gave deep insights into the topic, especially the way Sir explained about the aircrafts and aerodynamics of football in his first lecture revealed so many interesting facts. The second lecture Sir gave us about Reynolds Transport Theorem was totally an eye-opening session. He not only gave a technical talk, he also advised and gave suggestions on reading the illustrations in the textbook. According to the saying, the more you read, the more you will know. I'm pretty sure the precious knowledge that Sir inculcated into the students will definitely help our students in their studies and future. Once again, I would like to thank our guest for taking out time from his busy schedule and enlightening us with the knowledge. Thank you so much, sir. I would like to
Thank you,
extend my
thank you,
heartfelt
thank you, thank you, Lord.
I would extend my heartfelt thanks to our beloved Principal Sir, Vice Principal Sir, and HOD Sir for guiding and helping us to organize this lecture successfully. Last but not the least, I would like to thank all the faculty members, participants, and students for making this event successful. Without you, this wouldn't have been possible. Thank you all.